Hello everyone, my name is Swetanjal Datta and my roll number is 2017-1077. So the first part of the video report, we are going to look at the first question that we did for the assignment 2, and the first question involved us to plot the mean number of particles found in a particular energy state with energy epsilon and uh, epsilon minus alpha. So we are going to look at the details of what these symbols mean, and then we plotted these, and then we have made some simple observations regarding these quantum particles. So so science 2 started with sir teaching us about quantum statistics. So in quantum statistics, there are these three broad categories called Maxwell-Boltzmann statistics, and particles that follow this statistics are called the classical particles. And we learned about these particles in Science 1. Then there is the Fermi-Dirac statistics, and particles which obey Fermi-Dirac statistics are called fermions. And the last one is the Bose-Einstein statistics. And a part of this assignment was to make us go in depth about the Bose-Einstein condensate. And the particles that obey the Bose-Einstein statistics, they are called bosons. So now let us look at the broader picture. So we can assume that there's a three-dimensional box and there are n particles in this box. Now each of these particles have some position denoted by r vectors. So this is the set of all the position vectors of all the n particles, and they have some momentum, and that is denoted by this set of momentum vectors for all the n particles. Now if you freeze the system at a particular time instant, and then we go and measure the energy of each particular particle in this box. So we are going to find that each of these particles are in a particular energy level. So the lowest of this is E min and the highest is E max, and there is delta E separation between two energy levels. So we are going to find that each particle occupies some energy level. So we find that some particle occupies this particular energy level. So we go and stack that particle in this particular energy level. Then we go ahead again and measure the energy of another particle. Suppose we find it in this particular energy level. So we go and stack it up in this particular energy level. So, and this process continues. So once this is done for all the n particles, we'll find that each of the particles occupies some energy level in this hierarchy. Now the question is, at a particular energy level with energy epsilon r, what is the mean number of particles found in that particular state? That is the question that we have to study, and we were asked to make plots regarding these. So as derived in class, the formula for classical particles, that is the particles that follow Maxwell-Boltzmann statistics, is given by the following formula. This is the mean number of particles found at an energy level with energy epsilon r for classical particles. So this is the formula that governs it. Similarly, we had derived in class the formula for the mean number of particles at a particular energy level with energy epsilon r for bosons. So this is for bosons. And lastly, for fermions, we derived the following equation. So this is the formula for the mean number of particles found at a particular energy level with energy epsilon r for fermions. That is the particles which follow Fermi-Dirac statistics. So let us look at this plot. The plot in red is for classical particles or particles that follow Maxwell-Boltzmann statistics. The curve in purple is for particles that follow the Bose-Einstein statistics, and the curve in black is for particles that follow Fermi-Dirac statistics. So now one interesting observation is the bosons, or the particles that follow Bose-Einstein statistics. You can see that the curve doesn't touch the y-axis. So when at temperatures close to absolute zero, if you see, so you have a very huge probability, or rather a huge number of particles are said to be in a particular energy level. So you can see that as the temperature reduces to absolute zero, something like this. So the mean number of particles, since this is the plot for mean number of particles found at a particular energy level with energy epsilon r, you can see that this is infinity for bosons, but for fermions it is 0.5, and for classical particles it is 1. So for classical particles it is 1, for fermions it is 0.5, but for bosons, interestingly, this is infinite. And this is something which we are going to see in the last part of the video report, where we were asked to study about the Bose-Einstein condensate. So the takeaway from here is that at temperatures close to absolute zero, infinite number of particles, the mean number of particles that tend to be at a particular energy level with energy epsilon r is infinite.